I'm Jake Norgard.
I'm Emily Bodette.
I'm Jenna Bauer.
And I'm Tully Reed.
And this is our project about Olympic medal winners.
So here's our glossary. We're going to go over our executive summary, our business problem or question, our analytics problem framing, our data, our methodology, our model, and then our conclusion. So this is our executive summary. What we're trying to accomplish here is to determine if there's a peak performance age for different sports in the Olympics. So the way we decided to do that was by comparing the average age of all the data we had collected between all different sports and comparing that data to that of the ages of medal winners per sport. So first we took a pre-clean source of data from a reputable source that included our measures, which were names, ages, sports, countries, years of participation, and medals won for different Olympic sports between 2000 and 2012. We started grouping our data in a pivot table by age and medals won so that we could have a clean source of data to run a regression analysis on. After running a few regression analyses, we decided that this wasn't the best way to represent our data based on the data that we had, so we then decided to perform a z-test to determine the optimal medal winning age per sport, and then analyze this across each sport and comparing it to the overall average age of medal winners in the Olympics.
So for our project, we've decided to investigate the relationship between age and performance in the Olympics. More specifically, we want to find out if an athlete's age correlates with the numbers of medals they win and if it varies by sport. Because all of our group members are interested in athletics and the Olympic Games, this data set intrigues us and generates many questions. Having participated in various sports ourselves, we think it's important to know at what age athletes are at their peak performance in order to generate a time frame for success. Along with that, does the peak performance age differ between sports, or is there one age that people generally compete in when they compete in the Olympics?
Okay, so here's our hypothesis and analytics framing, and the question we wanted to answer was, does the average age for medal winning Olympic athletes differ by sport? And so we had a couple assumptions. The first one was that the average medal winning age will be different for every sport in the Olympics, and the next one was we thought there would be outliers in each sport because different people have different athletic ability. So we know that some people will perform better than others. So just a little context for ours, we knew we would need age as a parameter and we would have to determine the average age for every sport. And so we also decided that we would need to figure out the average age for every medal winner as well. And we decided to choose sports at random rather than using the entire population to better set the data. And the sports we chose was swimming, canoeing, gymnastics, alpine skiing, and equestrian. And so our null hypothesis was the average age equals average age per sport. And our alternative hypothesis was average age does not equal average age per sport. So this is a screenshot of the data we used, and it shows the metrics across the top. So we have athletes, average age of medal winners, age, country, year, date, event, and then the different medals and total medals.
To figure out if our hypothesis was correct, we decided that it would be best to run a multiple regression test on the sports that we selected. We looked at the relationship between age and number of gold, silver, and bronze medals won, but that didn't really give us the data that we wanted. So then we decided to put together pivot tables to group the data, and then we ran a regression on that again. It gave us better information, but it still wasn't conclusive. Finally, we then ran a z-test to see if the average age differed for all of our selected sports.
So now I'm going to talk a little bit about some of the assumptions within our methodology. As you can see, the relationship between X and Y is curvilinear for the most part between the sports, but not for every sport. As you can see, equestrian, there isn't really a relationship because it varies so widely, but there's a normal distribution for the most part between swimming. It's skewed to the right, which means we have outliers over in this section with the age of around 41. So we did have enough sample in this data set to use the central limit theorem, and that does apply to our situation. As you can see though, for swimming, the average ages range from 15 to 41 for medal winners, while in equestrian, the average ages range from 24 to 61. So we can already see just by looking at this data set without running any actual regressions and analysis that there is going to be a difference in age by sport. So now I'm going to talk about the model and how we ran our multiple regression. So the R value right here shows that 60% explains 60% of our variation. And as you can see, this is 16% up here for equestrian. So between the sports, there's lots of difference. In order for the relationship to be significant, we need to look at the p-values. So right here you can see that this is a significant number because it's less than 0.05 at 0.002. So for the gymnastics, our regression is looking okay. For equestrian though, our significance level is 0.14, which is well above 0.05. And then finally looking at the p-values for each variable, none of our p-values are looking very great in any of our regressions that we ran for all different 5 sports. And so it was hard for us to really use this data to make an accurate model to find what we were looking for. And continuing on to that, we couldn't really cut any of our data out because our p-values, none of them except for one on only gymnastics was above, they were all above 0.05, so none of them were significant. So that's kind of why our multiple regression analysis isn't working very well with our data set. So the only time that we were able to cut variables out was with gymnastics because there was one p-value that was less than 0.05. So when we did that, we did get a significance value of 0.0001, and then our p-value for bronze over here is looking a little bit better, which is showing that this data is significant for gymnastics.
So for the next part of our model, we decided to run z-test. After running multiple regression and adapting that to try and fit our data better, we realized that it was not really bringing back the results we needed to prove our hypothesis. So instead we decided to run z-test. We simplified our data by doing z-tests and comparing the total average age of sports. So for example, in gymnastics, our sample was 2,627, that was our sample size, and we compared that all sport number to the number of gymnasts and found the average age in those 2 samples in order to run our t-test. And we did this over the sports of swimming, canoeing, alpine skiing, gymnastics, and equestrian, which were kind of just random sports we selected that thought would help us prove our points on our data. Here's like a more specific model. We took alpine skiing. So since our sample size for both samples between like all sports and skiing were greater than 30, we used a z-test instead of a t-test for this data. We took the average age for each sample as x bar. So again, all sports was 27.05, and then skiing was 26.75, which as you can see are very similar numbers between these 2 sports. Since our critical value is less than the absolute value of our test statistic, we know we can reject the null hypothesis that all sport average is equal to the skiing average in this example. And then you can see our p-value here is between 0 and 1, but it's not the best value to show our data, and we believe that that is because our x-bar values for these 2 are very close in range. So in this example, it's kind of hard to find a significant proving factor that the data will always be different since the ages are so similar between these 2 data points.
So after running multiple regression tests and the z-test to compare the average age of the medal winners against the average age of all of the sports combined, we concluded that the average age of these medal winners does vary by sport.
So we kind of plotted that out in this graph so it's easier to understand. What we have here is the all sport average compared to all of the 5 sports that we were analyzing the whole time. And as you can see across the board, that generally the sports do differ by age. So that gives us the ability to reject the null hypothesis that average age equals average age by sport. So for example, if you're a gymnast and you want to be an Olympic medal winner, you might have to start earlier than if, say, you were participating in equestrian. In equestrian, you had the ability to be older and win gold medals, so that kind of gives a time frame for athletes to know when the peak time of their performance will be.
Thank you so much for watching our presentation, and we hope this presentation gave you a little bit more insight into when you can be successful in the Olympics.
Hey.